Good. So, hello. I assume that the purpose of this webinar is to give you a feel that mizer is a tool that you would be able to use. In this hour, of course, I'm not going to go into details, and that's why Elizabeth already announced this course where the details can be discussed. So why are we talking about mizer? Because we're all interested in managing our marine resources sustainably, and understanding the fishing and the fish is a big part of that, and mizer is a brilliant tool to get the necessary understanding of the ecosystem. So I'm going to divide my talk into two parts. Sorry, I need to actually figure out how I advance the slides. That didn't work so well yet. Let me see. There we go. Okay, I can now advance, but now I need to share with you again, I think. Right, so it'll be the what and the how. I'll start with what multi-species size spectrum modeling with mizer is all about. And I still can't advance the screen. Why is that? Now it works. Just so I feel reassured, can someone tell me if you are now seeing a slide that says mizer is an R package?
Yeah, you are. Okay, now.
Good. So mizer is an R package. That means if you've got R, you can easily use it. It's a package that's on CRUN, so you can install it with installed packages. Then you load the package, and then you can start using it. So here's an example of a function defined in the package. It comes with an example model for the North Sea, and here is a little picture that's created this way. There is, of course, a lot to mizer. It's got a web page where you can find out a lot about it. For example, there is a reference section where you see all the functions that exist in mizer, and you see it's a long, long, long list. But it's easy to get started, and you can become more powerful user as you go on. So you see already the start of this talk. I actually going to show you all the code necessary to do what I'm going to talk about. So let's look at this picture at the bottom in a little bigger to understand, first of all, what a size spectrum, a multi-species size spectrum model is about. So unlike most fisheries models that you will be familiar with that are age-based, mizer is size-based, and it keeps track of the abundance of all the species at all the sizes. And this graph here has the size of the individuals on the horizontal axis and the biomass density on the vertical axis. Each species has its own curve describing how the biomass is distributed over the sizes. So here, this curve, for example, they all start at egg size. So mizer models the entire life history of the fish. Of course, when you set up the model, you can specify what the egg sizes are, but most egg sizes are similar size. So by default, mizer just assumes they're all just a milligram. And then the biomass increases with the size. At maturity size, there's a little bump. That's where the individuals start investing some of their energy into reproduction, and therefore their growth slows down, but they continue to experience mortality. So eventually there'll be a maximum size where they don't grow anymore, and their abundance drops again, their biomass drops again. besides all these species spectra, there's also a resource spectrum in which we bunch all the stuff that's very small, right? So we're explicitly modeling only the larger species that we're actually interested in, and all the smaller species, including particularly the zooplankton and phytoplankton, we just model as a background resource with a very simple dynamics. So how do we know what these size spectra look like? So there is some sort of a mechanistic understanding of the fish behind this. So let me talk through the important principles. So first of all, the fish predate on smaller fish and on the resources of plankton, for example, according to a size preference function and a species preference matrix. So when you set up a model, you need to specify these feeding preferences of the species. This is important because the growth and reproduction can only happen due to predation on prey. Therefore, they are determined by the abundance of the appropriately sized prey. Similar predation is also an emergent property. The predation mortality is an emergent property because it depends on the abundance of predators of the appropriate size and species. Then, as I already said, this what the individuals do, how they grow, how they metabolize, how they invest into reproduction, that's all determined by the species-based physiological parameters of these individuals. And then through some nice math is translated to partial differential equations, and mizer simulates these partial differential equations. Last point is that recruitment is automatically density dependent in mizer, just because mizer actually models also the larval and juvenile stages, during which, of course, there's lots of competition and mortality due to predation. But also because, as we said earlier, the rate at which mature individuals can invest into reproduction depends on the abundance of prey. So there's competition there as well. So these are lots of multi-species interactions that are going into mizer. So one terminology, for example, about this growth being determined by abundance of prey, people call that the bottom-up control, and then that the mortality dependent on predators is a top-down control by the predators and the prey. So mizer includes all of that. So once we've got that all in our model, what can we do with it? We can now run scenarios to explore how changes in, for example, our exploitation affects the ecosystem. So I'm just running with you through the code that would be necessary to do such a scenario on this North Sea example model. I'm not saying that the North Sea example model that comes with mizer is particularly good and that the results we are achieving today are to be taken as perfect. By no means, but I just want to demonstrate the ideas. So there is this object that contains all the information about the model that is given to a function called project that projects the dynamics into the future. We want to run a scenario where the effort of the industrial fleet that targets as forage fish is increased with respect to the previous state of the model. That's probably makes sense to those of makes sense to expect that there is multi-species effect. So if you reduce the abundance of forage fish, that's probably going to have an effect on the predator fish. So let's see what will happen. We say that we want to project this forward for 20 years. running this function returns an object that contains all the information about the time series. And we can, for example, look at it with the animate spectra function, which produces something like this. So I just press the play button. And you see as the years progress, how the size spectra change. So let's step through this a bit more slowly. We've got here the sand eel. Sorry, the pops up sound working too well, but the sand eel, and there's the pout, and there's, I think, the spread, and they go down. So after 1 year, their abundance at the large sizes where they're being fished has gone down. After a while, this will of course have a knock-on effect also on their recruitment. But as we now go on, take a look over here. Well, actually, let me zoom in a little bit so this becomes. Oops. My cursor isn't doing exactly what I expect it to do due to zoom. Okay, so let me not try to zoom in. If I play this, you notice that the species over here, the abundance in this region of the size spectrum also change. So that's sort of what we expected, that the predators react to change in it. Right, so let's look at this in other ways. For example, we can plot the biomass over time. So looking at the entire size spectrum was a bit overwhelming. Let's assume we're only interested in the total biomass of each species. Then we can make a nice time series plot. And indeed, the sand eel goes down, the North Sea pout goes down, the spread goes down. The gurnard goes up a little bit, but it would be really nice to see the relative change, the percentage change, rather than these absolute numbers, because of the very large range of biomasses of the different species, very difficult to see. So one important thing in a tool like mizer is having lots of nice ways of visualizing the results. And that gives me the opportunity to say that mizer is not just one package. There is a whole family of mizer extensions that provide extra functionality. So there's, for example, the mizer experimental package, where new code can go quickly and then be refined. And I'm loading that package now because it has a function called plot the biomass relative, which plots the relative change in the biomass over time. And so, as expected, we see that the now more heavily fished species go down in abundance, but some other species benefit from that fishing on the forage fish. We might actually be more interested in the change in the yield. So there's a function to plot the relative change in yield over time. And now this picture is actually quite interesting. But let's not dig into the details right now, partly because my cursor isn't selecting the right places when I hover over it. But it's interesting things are going on to do both the competition between the species, but also to do with changes in predation. And without having coded these effects into a mizer model, I think by pure thought, it's impossible to think through this as well as with mizer. Right. Okay, how the years, let's swap that and let me take a breather, a quick break. I'm now going to switch to talk about how you could set up your own mizer model to do similar explorations. So before I do that, I want to make sure there are the principles of what the size spectrum modeling is are sufficiently clear and motivated. So I'd love it if anyone had any questions. So I don't actually know. Oh, thank you. I don't know how this audience selected itself. It may well be that you were all quite well motivated to be interested in size spectrum models to start with, which is helpful. So then let's go on. So my aim, as you recall, is to get across that this is something that you can easily use yourself. So let me now start talking about how to set up a model yourself. So I'm going to share my screen again. So you need to, again, my slide advancement doesn't work. There we go. So first of all, you need to collect some information about the species that you want to include in your model. So you create a data frame with the species parameters, one row for each species, one column for each parameter. There's a whole range of species parameters that mizer can understand and use, but here we're just going to use a rather minimal set. We're going to specify the maximum size and the maturity size of the species. That's something you could look up on FishBase, for example. We are going to use the von Better-Landvik growth curve parameter to inform mizer about how fast growing the species are. We are going to use the A and B parameters that allow us to translate between length and weight, because as you've seen in the previous slides, mizer likes to use the weight in grams as the measure of size, but in for some purposes, it's the length that is the natural variable. For example, size selectivity of gears is usually done in lengths. So we have these parameters to convert to length, from length to weight. Then we specify the preferred predator-prey size ratio, right? So one of the ideas behind mizer is that the fish of a particular predator species likes to feed on prey that are a certain fraction of its own size, and this fraction is species dependent. It depends very much on the physiology of the fish, on the geometry of the fish. So there's a parameter beta that gives this preferred predator-prey size ratio. It's a bit difficult. This is not something you can easily find on FishBase. You can either get an idea by studying the diet, by studying stomach contents, or you get an idea by just thinking about how big can stuff be to fit into the mouth of the predator, and how small can it be and still be retained by the gill rakers, say. So you need that. And then observe biomasses and observe fisheries yields. So for this talk, I've got a demo species parameter data frame, which I'm just reading in. And here it is. We also need to specify the fishing gear. That too goes by preparing a data frame where for each gear and each species targeted by that gear, you specify the fishing mortality exerted by that gear on that species for the fully selected individuals. But very importantly, you also specify the size selectivity of the gear. So in this example, we actually just having one gear, which we call main. There's some fishing mortalities in the catchability column. And then we're using a sigmoidal curve for the selectivity function, and the L50 and L25 are the lengths at which that curve reaches either 50% or 25%. There are many ways of specifying the gear selectivity, but here is a simple one that we run with. Now, one thing to say now, if you now say, well, I don't know my selectivity of the gear, does that mean I can't set up a mizer model? No, just come up with some numbers, because you'll see in a moment that we're going to change those anyway. Right, once you've got these two data frames, you can use this new multi-species Brums function to create a mizer Brums object that is sort of encapsulating the model. Actually, we also specify a fishing effort. So when I said the catchability is the fishing mortality, that's when the effort is 1. We have the effort as a way of changing the fishing effort later, which will, of course, change the fishing mortality. Right, so that once we've got such a Brums object, we can, for example, plot the size spectrum. And now this doesn't look like the kind of size spectrum that you'd seen earlier. That's because initially, mizer just sets up some arbitrary initial conditions. What we now do is just run the dynamics to a steady state. So if we start with this initial condition and run the dynamics, things will evolve. And using the function steady, it runs the dynamics until things have settled down. At that stage, the spectrum looks like this. Still a bit weird and still very ugly. And one reason is that it hasn't taken the biomass information into account yet. This plot here, created a plot biomass versus species. For each species on the horizontal axis, it plots with a open circle the biomass that is currently in the model, and with a filled square, the observed biomass that we had put into the species parameter data frame. And they don't agree at all. Mizer just hadn't used that information when it was setting up the model so far. Not a big problem, because there are functions to fix that. First of all, there's one function that just sets the overall scale of the model without changing anything substantial. That can be used to just get the average biomasses correct. But you see then some species will still be too abundant and others not as abundant. There's another function called match biomasses, which is now just going to rescale all the abundances to get the biomasses spot on. That, of course, is cheating. The result will not be a steady state anymore. When the system will very quickly run away from that rescaled state. And actually, you need to then run the steady function again. And that will spoil all your biomasses again. But no problem, you just iterate this. You do this a couple of times or 3 times. And you will end up with a steady state that has the biomasses that you observed, right? Because each time you rescale the abundances, that has rescaled the spawning stock biomass, that has given a different reproduction rate that when you then run steady is kept fixed while running to steady state, creates a new configuration, which because everything is reorganized due to multi-species effects, will not be spot on. But luckily, if you do this over and over again, the process converges and you've got a state that matches observations. But so far, we've only matched the observations of biomass. There are other observations we have. So for example, in our example today, we're going to assume that we've got the size distribution of the catches. So I prepared a data frame which for 1 centimeter large size classes has the number of observations from the size of landings, right? You know that people will go and take samples from the landings and measure the sizes of the individuals there, and that's where this data comes from. So for some surprisingly small 2 centimeter blue whitings, 2 of them actually in this. But then the numbers will increase for intermediate size classes, and down here I plotted the larger size classes. There's actually 1 cod that's 1.60 meters. So of course we don't like to work with lists of numbers. Mizer's got a nice function that plots this yield or catch versus the size. So we've got the size in centimeters down here. We've got in blue the curve that corresponded to the data that we just imported. And we've got in red the size distribution of the catch that the model calculates. We've also got in gray the abundance of the species. But it's the red curve that we're interested in, which shows us that the model doesn't quite capture what's going on in the real world. And that's because we got the selectivity wrong. So we had said that our gear starts fishing the blue white. Oh, so this is the example of blue whiting. I just chose that randomly. For blue whiting, we said that already at 14.8 centimeters, 50% of the individuals are being caught. But that's clearly not the case. So we need to, but no disaster. We can now change these parameters. So that's the spirit I want to get across in this talk, is that you can quickly build a model. Then you can compare the model output with observations, and then you can fix the parameters where you got them wrong. For example, in this case, we could try to change the selectivity of the gear to not fish the small individuals. It still doesn't fit over here. The model says we're catching very many large individuals. That's because there's not enough mortality on those large individuals. So we probably need to revise our fishing mortality. And so you already see that this is going to get a bit tedious, writing all these commands for making changes to the parameters, making the plots to compare with observations. So luckily there is a very nice shiny gadget included in mizer experimental that allows us to do that with point and click. So generally I hate point and click. And so it's important to me that in mizer I can do everything by the command line or by programming. But for some purposes where, for example, I just want to get the right parameter values in the params object, I really like this gadget. So I'm going to stop this and now share the gadget itself with you. Any questions at this point? I see there's another one in the chat. Is FishBase an online resource for accessing values for these parameters? I'm not familiar with it. Yes, so FishBase is a online database with a web interface, but also an R API interface that contains for a huge number of species, huge number of known facts and known parameters. Just Google for FishBase and you'll be amazed. The challenge with using FishBase is that it's for the entire world. It's got observations from all over the place, and it takes a little while to make sure that you choose parameters that are appropriate to your particular area. So and also not all observations of the same quality. It's wonderful to talk about fish base. So that was the question from the chat. Now I'm going to share the gadget for tuning the model. So there's a lot on the screen now. On the right, there are a number of tabs. Each tab shows different kinds of plots. On the left, there are a number of controls with sliders where I can change the model parameters. So for example, there's a tab that shows the abundance, and this is a plot we'd seen previously. We've actually currently made sure that the observed biomasses and the model biomasses are quite close to each other. There is a tab that shows growth curves. I can do it so that it shows the growth curves of all of the species, but let's concentrate on this one, which looks a bit wrong. So I've now zoomed into the monkfish. There are two curves in this upper plot. One is the growth curve that is actually realized in the model, because remember in the model, the growth is an emergent property depending on the availability of prey. The other curve is the von Bertalanffy curve. And we're currently just assuming that the von Bertalanffy curve is the real world. Of course, these are always just fits to actual size and age data. But anyway, let's assume that we believe that this model growth is too high, too fast compared to what we believe to be the truth in the system. Well, there are model parameters that we can change. They're model parameters that can't be observed directly, like, for example, the what are we doing? The predation rate coefficient. If we decrease that, the species predates less ferociously and therefore gets less energy and therefore grows less. There's also a parameter that gives the maximum rate at which the fish can digest food. If we decrease that, it will also decrease the growth because the fish will be more satiated and therefore not taken all of the available food. And you see, we can just change these sliders until we believe that the model is close enough to the truth. How did I decide which of these parameters to change? I was actually looking at the feeding level down here. The feeding level expresses how satiated the individual is. Feeding level of 1 means they're completely satiated. If you give them extra food, they will just ignore it. Feeding level of 0 means they're not getting anything. They eat everything they can get. This gray line is the critical feeding level that they need to at least feed at that level in order to sustain their metabolism. Just as a guide, I'm trying to keep this feeding level somewhere, 0.6 or 0.7, about that range. But if you've got a species which in your system is always satiated, we would increase that. Okay. So we've changed the growth parameters. Let's look at the abundance. Because we decreased the growth rate, but that has decreased the abundance of the species as well. But of course, we can just scale this up with the metric. So what we did with the biomasses function earlier now has a button to do it. Finally, we need to run to steady state. Good. So now we've got growth curves that look nicer. Other tabs we have are the catch tab. Let's go to the catch tab and let's select the blue whiting. This is where we already tried to fix the agreement with the model catch and the observed catch size distribution earlier. You also see that the absolute yield is too low in the model compared to the observed ones. So that we're going to fix by fixing the fishing mortality. I don't know where this very low value came from. It's clearly too low. Let's increase that a little bit. That has both brought the observation closer in line with the model up here. It's also made the size distribution match more closely because the increased mortality has decreased the abundance of large individuals in the sea, and therefore also the number of large individuals in the catch. So you can now play with this for as long as you like. You can also now change the selectivity parameters, play with different fishing mortalities. But you need to remember that other things change. So, for example, because we've now increased the fishing mortality, the abundance of the blue whiting has gone down again. So let's put that back up to where we want it to be. And also, we always have to remember that we need to run to steady state again after changing parameters. Okay, that has made minute changes to the other species. This looks pretty good. Now, other things that's worth looking at is, for example, the diet. Everything's size-based in mizer, so the diet too changes as the predator grows up. They change what they feed on. The smalls, they say, the 1 gram blue whiting has to eat almost exclusively on the small stuff that we bunched into the resource. So they probably feed on zooplankton at that size still. The very large ones here, up here we've got 700 gram blue whitings. They get about half the diet from fish now. Now, I know nothing about blue whiting diet, but if you know that actually blue whiting, when they get about 100 grams already, their diet is composed to 50% of fish, then you know that you got the predator-prey mass ratio wrong. So let's change that. Yes, beta. So currently we had a predator-prey mass ratio of 466. So the blue whiting prefers to eat on something that's 466 times smaller than itself. Maybe that was overestimated. So if you change it to something smaller, you see each time I decrease the predator-prey mass ratio, the amount of fish in the diet goes up. Let me not talk about the complicated diagram at the bottom. This is enough. I think actually this is enough. You now got, I think, the idea. So I am going to go back to my talk and give you my take-home messages before we can go into discussions. So my take-home messages are A, that mizer is a good tool that allows you to investigate different ecosystem-based management scenarios, right? When you make changes in your fisheries management, it will have an effect on other species, and we've seen examples of that. That's pretty powerful. There are, of course, other models that can do this, for example, Atlantis. But compared to other models, setting up a mizer model is really easy, right? We've just done it together. We haven't tuned it to all possible observations perfectly, but we've got something initial to work with. Right. So the third point is actually quite important. You learn a lot about the ecosystem while you're setting up and tuning the model. For example, well, actually, I should have gone on a little bit. You will, if you look at the different species, you will notice that some species are actually not quite viable. In order to maintain the fishing yield that is observed, they will struggle in the model because they have too much mortality on them. So then you know that actually there's something wrong with your parameters. Either you underestimate the growth of the species, or you have thought that it's being predated on by some predator species that actually doesn't live in the same area, so it doesn't overlap as much. So you would change the species interaction matrix to fix that. Setting up a mizer model helps not only to run future scenarios, it also helps you to find discrepancies in your data, but it also sometimes points out that some species, there's something interesting going on that you hadn't been aware of. Okay. So all of this now is to motivate that it's worth digging deeper into mizer, and I can advertise the next online mizer course starting on the 7th of November. We've run such a mizer course for a different with a different emphasis already. We've organized it into 3 weeks, where the first week is about gaining a deeper understanding of the whole size spectrum idea. Week 2 is about building models, and week 3 is then about using those models to run scenarios. So the sign up is currently ... We'll share it with you, and luckily Elizabeth just puts the link into the chat where you keep updated on the SNMI events, and the the course will show up there shortly. Right. So, any comments, any questions?
Hi, Gustav. Hello.
Hi, Gaetano.
Hi. Yeah, thank you. This was a very nice and interesting overview and of using mizer. I just had a question. Probably I missed it. Probably it's more a curiosity about. At the beginning, you showed like a scenario, increase in effort of. Increased effort of catching a specific species. I was wondering, I mean, and you can also control the effort in your model for each of the species, but I mean, this increased effort, on what information within the model goes to impact? I don't know if it's clear. I mean, on the catch, on the yield, or on, yeah.
So you were right. What I changed was the effort on a particular gear. So the effort is something that is specific to each gear. So each gear, you can control the effort for each gear separately. But that's just a choice of mizer to talk about gears. If you prefer, you could talk about fleets. So we've got an industrial fleet, for example, set up already as a gear that targets only spread, sand eel, and northern pout. And it was set up with a certain knife edge selectivity. So rather than a sigmoidal switch on, it's a sharp switch on. I don't know why. And a certain catchability. Now, the fishing mortality experienced by an individual in the model will be the product of the catchability and the effort and the selectivity factor. So in this case, we've got knife edge selectivity. There will be no fishing mortality on spread smaller than 13 grams, I think it is, yeah. And there will be, with effort 1, there will be a fishing mortality of 1. In the, previously we had a model with a effort of 0 on, I didn't show that, but it was set up with an effort of 0 for the industrial fleet. So there was no fishing mortality on spread and sand eel before. And that's actually why they stuck up their head so much over the initial size spectrum. The reason why this abundance keeps on increasing for larger and larger sand eels was because the large sand eels didn't have much mortality because they weren't being fished at all. After you actually start fishing them, they look more like the other species too, that turn around more early. Now, I don't know whether I all talked in the direction of your question, but ask your question again.
No, yeah, I mean, I get it. So yeah, the effort is you have a level of effort related to each fleet or years that you have in the model, basically. But the effort itself is quantified how? I mean, it's like in, I don't know, days at sea or.
Yeah, so this is a bit up to you to choose, because the fishing mortality is just the product of the catchability and the effort. So the way I usually do it is I say, well, the current effort, the status quo effort, I just call that effort equal to 1, because then the catchability will be the current fishing mortality. And then I use the effort to encode changes away from the current situation over time. But you could choose, if you have effort in some nice units, then you can do it that way as well. That will just mean you have to make your catchability different as well.
Okay, thanks, Gustav.
You're welcome. So my aim was not necessarily so much to get each of you to be an expert in setting up a mizer model for your interests. One thing you could do is see if you've got some project student or even some PhD student or who needs a nice project and can be asked to set up a mizer model for you, and send them to the course in November. I'm doing that with one of my students. And there's a question from Lorna, when roughly the link to sign up will be available. By Monday. Good. You know how to get in touch with me, probably. If you do get into mizer, always know that I'm interested in hearing what you're doing, the problems you're running into. I may have made it seem today like there won't be any problems or challenges. There will definitely be many challenges and things to discuss. And I'm always happy to receive emails.
Great. It might be useful, Gustav, if you could put your email in the chat, just in case anyone wants to get in contact with you.
Good idea.
This will also be available on the YouTube channel to go back and watch and everything. And yeah, we'll be in touch soon, either putting the sign up link on the SMR calendar, or it'll be in the newsletter or on social media. We're SMR UK on Twitter. But any more questions, either get in touch with Gustav, and any questions on the SMR end and about the course, just drop me an email and I can always send you the link I will put my email in the chat too. And
the annoying thing is the chat is completely gone once we log out, isn't it?
Yes, yeah, that is true. But if you go through the SMR channels, you should be able to get in contact with us. Well, I'm happy to do that. But I hope everyone has enjoyed the course.
And Google a lot for mizer, because eventually Google will learn that mizer is not just some crazy group somewhere. Whatever comes up for you initially, after a while it learns that mizer is a fisheries model.
Awesome, brilliant. If you're happy to leave it there, Gustav, we'll let everyone get on with the rest of their day. But thank you all for coming, and I hope you found it useful.
Thank you very much. Bye.
Bye, everyone.